Okay, so in this video we are going to be looking at the graph of y equals the square root of x. And looking at this graph shape also necessitates further conversation about transformations, because we now need to think about the two transformations that we omitted in the earlier video, that is the dilation from the y-axis and the reflection in the y-axis. But let's first of all start with the basic shape of y equals the square root of x. And so y equals root x, again, if you were to plot out some points, when x equals 1, square root of 1 is 1. When x equals 2, square root of 2 is root 2, which is about 1.4. When x equals 3, square root of 3 is about 1.6. When x equals 4, square root of 4 is obviously 2. And we can jump ahead to the next nice square number. When x equals 9, square root of 9 is 3. Okay, so we get this graph, which actually has a connection to the parabola. So the square root is the opposite or inverse operation to squaring, and the square root graph is the inverse graph of a parabola. We'll learn more about inverse functions in the next topic. If we were to have, y equals x squared, now the scale's not nice and square here, but y equals x squared would go this way, y equals the square root of x goes this way. Obviously y equals x squared, we also have the other half of the parabola, and that other half of the parabola would be mirrored down here if we were looking at the whole, sorry, I'll try and get it sort of symmetric. If we were looking at the whole, it's not going to be there, is it? It's going to go through there, and then obviously further off. So it is still a parabola in terms of shape. Okay, it's half of a parabola, the square root. As I said, we'll look at inverse functions a bit further on in this topic. And we will look at that in a bit more detail. But in terms of shape, you do want to think about it being a parabola, half of a parabola on its side. The square root graph only exists for x values when x is bigger than or equal to 0. Okay, so it only exists over here on the right-hand side of the y-axis. Okay, now that is until we do some transformations to it. We could translate it this way, and then it would exist back here. But just y equals the square root of x only exists when x is positive, and that's because we can't take the square root of a negative. If you were to look at when x equals -1, y equals the square root of -1, well, that's not defined, and that's why there's no graph back here at -1. Okay. Similarly, when x equals -5, that's not defined, so there's no graph back here at all. And therefore it also only exists for y values where y is bigger than 0, so it only exists up here in the above the x-axis, and again that's because when we take the square root, and that is it's the positive square root. Okay, if the equation was y squared equals x, then we would be looking at y equals the positive and negative square root of x, which, if we think about that in terms of our transformations, it's two graphs. It's y equals positive root x, and it's y equals negative root x. Now, we know that when we stick a negative in front of a function, that's when we reflect it in the x-axis, and so that's when we're seeing this bottom half of the parabola there. So if we were looking at the graph of y squared equals x, that would be y equals both the positive and negative square root of x, and we would have the whole sideways parabola. When we are just looking at y equals root x, implied in that, in the same way that when I write the number 3, I don't mean plus or minus 3, I mean positive 3. If I want to mean negative 3, I have to write negative 3. So when I just write root x, I don't mean positive or negative root x, I just mean root x, so the positive square root of x. And so therefore when we take a positive square root of a positive value, we will also have a positive value. And therefore our whole graph is only existing in this top right quadrant where x is positive and y is positive. As I said, we can then apply transformations, reflections, dilations, translations, and the graph can end up all over the place. Could end up down here over this way, the same shape. But that's because if you were to substitute, we'll talk more about that, but if you were to substitute negative x values into that, you wouldn't be taking a negative square root. We'll have a look at that when we get to it. So let's start with the transformations that we're already familiar with. So this list of transformations here are things we've discussed in isolation. We've now looked at them in the context of the hyperbola and in the context of the truncus, and we now want to think about how that applies to our square root graph. So we know that when we dilate by a factor of a from the x-axis, it is when we multiply the whole function by a. In this case, f of x is the square root of x, and so multiplying the square root of x by a is a times the square root of x. So that would be a dilation of of the square root graph from the x-axis by a factor of a. Okay, so therefore, multiplying each value by the same quantity. So we would get a sort of taller square root graph. Reflecting in the x-axis, we know is when we multiply the whole function by -1. So if our whole function here is square root of x, reflecting it in the x-axis is negative square root of x. We just talked about that one previously. Translating to the right by h units is when we replace just the x part of the function with x minus h. So just replacing the x part of the function with x minus h is just replacing under the square root. So square root of x minus h will translate to the right by h units. And then translating up or down is when we add on to the end of the function, so outside of the function. So y equals square root of x, no change to that, and after that we add on k. That would translate our square root graph up. So if we were to have y equals the square root of x plus 3, that would go up by 3, and we'd be looking at the same shape sitting up here. If we were to look alternatively at the graph of y equals the square root of x minus 2, that goes to the right by 2, and so we take this shape and we translate it to the right by 2, and it would be over here. Okay. As I said, if we did x plus 2, that goes to the left by 2. The shape translates to the left, and we have our graph existing over here. But that's because, for example, if you were to sub x equals -2 into that, that doesn't make the whole thing underneath the square root negative. -2 plus 2 is 0, and square root of 0 is 0. If you were to substitute -1 into that, okay, you've got square root of -1 plus 2, which is the square root of +1, so there's no problem with taking the square root. You're still taking the square root of a positive number, even though you're including some negative x values in that. Okay, and then obviously combining those together, we could have y equals a, so our dilations and reflections from the x-axis, times the square root, sorry, just write that a bit smaller, square root of x minus h, so translations left and right, plus k, translations up and down. Obviously that would be the same as writing it as k plus a times the square root of x minus h. So, you can write it the other way around as well, it's still the same thing. Just to be aware of, just be careful about when you write square roots that it's not ambiguous about where your square root's ending. Is k under the square root or not? Okay, make sure it's really clear that the plus k is separate. Okay, which is why sometimes you might see it written at the beginning, because that helps to avoid that ambiguity. Okay, so as I said, there's two other transformations that we haven't needed to consider before now, and I'll have a bit of a look further on at why we haven't needed to consider these before now. But in the context of the square root graph, we need to start to think about these. The first of those is the reflection in the y-axis. Okay, so the reflection in the y-axis means that the x-coordinate of every point is multiplied by -1, and that's therefore going to then reflect around the y-axis if you multiply the x-coordinates by -1. So we're already familiar with the reflection in the x-axis. We know that's when we multiply the whole function by -1. So for our square root graph, that's y equals negative square root of x. When we reflect in the y-axis, we only multiply the x part of the function by -1. So in this instance, that will be y equals the square root of negative x. And I can hear some of you thinking, oh, but we can't take square roots of negatives. But that's why, if we have a look at what that graph is going to look like, if we draw the square root of negative x, it's this graph reflected in the y-axis. So let me plot out some points and then let's talk about that. So it's going to go through -1, 1, it's going to go through -4, 2, and actually this is the point. If you let x equal -4, when x equals -4, you have y equals the square root of -4, which is the square root of +4, which is 2. So as long as the x value is negative, you're not square rooting a negative by putting a negative sign under here. Okay, so what we're going to see here is when we reflect this graph in the sorry, it's not there, it's at 9. Sorry. When we reflect this graph in the y-axis, okay, our shape is going to go that way. Just let me get it so it actually hits through those points, sorry. Why my screen is so wobbly today. It's not getting much better, is it? Alright, let's go with that. Pretend that's a smooth line. I don't know why. Let me try it if I go this way. Bit better. It's a bit wobbly at the end there. Pretend it's straight. Well, not straight, but smooth. So what we're seeing here is when we reflect the graph in the y-axis, it only exists when x is less than or equal to 0. It only exists back over here to the left of the y-axis. And that's because the only way that this function will exist is if we put a negative value as x, because then we're doing negative negative, so it's a positive number under the square root, and it's still possible to square root that. Okay. So the question here, I jumped ahead here, we've got the graph of y equals x is shown below, so that's drawn in red. We want to sketch the graphs of y equals negative root x, which is the reflection in the x-axis. So that one's going to go down here. Let me plot those points out. Okay. So this one down here, so it's y equals negative root x down there. The graph of y equals square root of negative x, that's the reflection in the y-axis, that's this one. Yeah, sorry, I'm going to need to do some screen calibrating, I think. And then finally, this, if we think about this one, y equals negative square root of negative x, well, that's just doing both reflections. So if we reflect in the x-axis and then reflect in the y-axis, or we could think about it the other way around as well, reflect in the y-axis and then reflect in the x-axis. So the shape we're going to get here is going to be this one here. We've still got problems, haven't we? Okay. And so that would be y equals negative square root of negative x. So we'll talk more about this further down the track, but when you're sketching a square root graph, that's the first thing I want you to identify. What reflections have happened, and therefore which of these four shapes am I dealing with in my particular graph? Then worry about dilations and translations. Okay? Alright, so reflecting in the y-axis is f of negative x. Okay, so we actually haven't had to worry about this before now, and let's think about why we haven't had to worry about it. If my function is f of x equals x, as it is here, okay, then f of negative x is equal to, so we replace the x's with negative x's, so it's just going to be equal to negative x. And therefore, that's actually the same as negative f of x. Okay, it's not different. So reflecting for the linear graph, when we reflect it in the y-axis, we get this line here. Again, apologies for the slightly wobbly lines. That's a screen issue at the moment. If we reflect it in the y-axis, we actually end up with the same graph as if we had reflected it in the x-axis. So we didn't have to think about reflecting in the y-axis for a linear graph. We could just always describe it as a reflection in the x-axis. If we think about the quadratic, okay, so for the quadratic function, f of x is x squared. If we want to reflect that in the y-axis, f of negative x means replacing all the x's in the original function with negative x's, and so we have negative x squared, and negative x squared is negative x times negative x, which is just positive x squared. And so this is just the same as f of x. So when we dilate in the y-axis, we find that it actually just equals the same thing, and that makes sense graphically. If you reflect this shape in the y-axis, it's symmetric about the y-axis. So you actually get the same shape. So we certainly didn't need to think about the transformation of reflection in the y-axis when we were looking at the parabola. If we think about the cubic shape, again, if we have f of x equals x cubed, then f of negative x is negative x all cubed. And if you've got negative x all cubed, it's negative x times negative x times negative x. So it's just negative x cubed, which is negative f of x, which is same as the reflection in the x-axis. So for the cubic, reflecting in the y-axis is the same as reflecting in the x-axis. We found the same here for the linear. Reflecting in the y-axis ends up being the same as reflecting in the x-axis. That's not true for all functions. We see over here that reflecting in the y-axis is the same as the original function. But we saw up here that reflecting in the y-axis produces a whole new shape. And so we have to think about it as something separate. Okay? So if we were to imagine reflecting this shape in the y-axis, so taking each point and mirroring it across the y-axis, so negative 2, 8, still goes through 0, 0, negative 1 becomes positive 1, negative 1, negative 2, negative 8 becomes positive 2, negative 8, and we actually get reflecting it across the y-axis, which was actually what I did this, okay, it actually ends up being the same as if we had reflected it in the x-axis. Okay. So again, we didn't need to think about it as a new transformation when we were looking at the cubic graph. Similarly for the quartic, I know we haven't talked a lot about the quartic, we'll talk further about that later, but you might have met it last year. So if we're looking at the quartic function as f of x equals x to the power of 4, then reflecting it in the y-axis is f of negative x, which means we get negative x to the power of 4. And again, because it's an even power, you're multiplying x by itself, negative x by itself, sorry, an even number of times, so the negatives will all cancel out. You've got negative x times negative x, which is positive x, times positive x squared, times negative x again, which is negative x cubed, and then times negative x again, which is positive x to the power of 4. So this is just the same as x to the power of 4, which is f of x. So again here, reflecting in the y-axis results in the original function. And we can see that. This is another shape that is symmetric about the y-axis. So if you reflect it in the y-axis, you get exactly the same shape. Okay? The algebra supports that and the graph supports that. Alright, let's think about our two newest functions. We still didn't need to think about reflecting in the y-axis for these. If we think about the hyperbola, so if we think about f of x as being 1 on x, when we reflect the hyperbola in the y-axis, f of negative x, so that's 1 over negative x, but that's the same as negative 1 over x. A positive divided by a negative is a negative. And so again, this is negative f of x. Okay? Reflection in the y-axis for the hyperbola ends up being the same as reflection in the x-axis. And we can think about that. If you reflect in the y-axis, this point goes here, this point comes here, we can reflect a few other points, and we're going to have something along these lines. Okay, we can reflect a few other points across the y-axis, and we're going to have something along these lines. And essentially, we get the hyperbola shape happening in this top left and bottom right quadrants, which is the same thing that would have happened if we had reflected in the x-axis. Okay, so same thing graphically happens, regardless of whether reflect in x or reflect in y. So again, we didn't have to think about reflecting in the y-axis for the hyperbola. And lastly, for the truncus, so we know the rule for the truncus is 1 on x squared. Again, if we reflect that in the y-axis, so f of negative x, we replace the x in the function with negative x. But again, negative x all squared is just x squared. And so this is just f of x. So for the truncus, reflecting in the y-axis is just the same as the original function. And we can see that graphically as well. If you reflect all of these points in the y-axis, you're going to get exactly the same graph because it is a graph shape that is symmetric about the y-axis. Okay. Alright, so that's why we haven't talked about it before now, but now for the square root graph we see that when we reflect in the y-axis we don't get the original function, and it's not the same as when we reflect in the x-axis, so it's something new and separate that we have to be able to think about. The second transformation we have to add in is dilation from the y-axis. Okay. So we're all already comfortable with dilation from the x-axis, so that's these two. We know if we dilate from the x-axis by a factor of a, we do a times f of x. We know if we dilate from the x-axis by a factor of 1 on a, it's going to be 1 on a times f of x. Okay, they're already comfortable. We're happy with those. We know what's going on there. Okay, so we know that for the square root graph, dilating by a factor of a from the x-axis is y equals a times root x. Dilating by a factor of 1 on a from the x-axis is y equals 1 on a times root x. I'm just going to pause and jump over to a graphing program, because dilating from the y-axis is a bit like reflecting from the x-axis. So we know when we reflect in the x-axis, the negative goes out the front. When we reflect in the y-axis, the negative goes inside here. It happens to the x value. Okay, so the same thing is dilation from the y-axis is also when we're multiplying not the whole function by a number, but just the x part of the function by a number. Okay, I'm going to pause the video and just jump across to a graphing program and just sort of have a play around and show you what happens as we change that value in front of x. Okay, so here we are here with our square root graph. So there's a black line underneath that red line, which is just y equals root x, and then the red line, I've got the equation over here on the left, is y equals the square root of n times x. Okay, so that is f of nx. Okay, we're just multiplying the x part of the function by n, not the whole function by n. So if we multiplied the whole function by n, it would be n times the square root of x. Just multiplying the x part of the function by n, it's the square root of n times x. Okay, so if we have a look at what happens here when as we change the value of n, sorry, just let me grab my, there we go. So as I increase the value of n, let's have a look at what happens. So we're expecting this to be about dilation from the y-axis as we increase the value of n. Again, I want you to be clear about how you think about it. It looks like it's stretching away from the x-axis, which in some ways it is. We'll talk about that connection in a bit. But if we look at what's happening compared to the y-axis, so this way is what's happening, okay? This way is what's happened compared to the y-axis. As we're making n bigger, the graph is not stretching away from the x-axis, but it is getting closer to the x-axis. Okay, let me just get rid of those arrows because it's hard to rub them out here. So for example here, when n is 3, okay, my graph is closer to the y-axis. It hasn't been, so the x-coordinates haven't been multiplied by 3. It looks like instead, without giving anything away, perhaps you're speculating, but in fact what's happening is they've been divided by 3. Okay, we've divided by 3, so that's going to be 4/3, 1 1/3, divided by 3, that's 1 divided by a third, 1 times a third, sorry, so that's, yeah, 1 divided by 3, which is a third. Okay, it's off the scale here, but it would have gone through 9, 3, and so it's now going through 3, 3. The scale's slightly out there, I think. Oh, it's because I'm at 3.1. Sorry, let me make it 3. There we go. Now it does exactly go through 3, 3. So it's being not stretched away by a factor of 3. It's being squashed in by a factor of 3. Now we don't differentiate between stretch and squash. Dilation is the one word for that. So the dilation factor is going to be something less than 1, or between 0 and 1 if it's a squash. So the dilation factor here isn't by 3, the dilation factor is by 1/3 from the y-axis. Let me just get rid of those arrows, they're hard to erase if I don't undo them. Okay, let's have a think about then what happens. So let's put n back to 1. Okay, so we have y equals root x. So if we were to make n smaller than 1, we expect that the graph stretches away from the y-axis. So if I make n 0.5, for example, the graph has stretched away from the x-axis by a factor of 2. Away from the y-axis by a factor of 2. The x-coordinates have been doubled. Instead of going through 1, 1, it now goes through 2, 1. Instead of going through 4, 2, it now goes through 8, 2. Okay? So we are dilating by the reciprocal of n from the y-axis. Remember, reciprocal is a word we use when we're flipping the fraction, swapping the numerator and denominator. So if n is 0.5, which is 1/2, what's actually happening is a dilation by 2 over 1, so by 2 from the y-axis. Okay. Again, let me just delete those arrows. So if I continue to make n smaller, it continues to stretch further away from the y-axis, so it becomes flatter. If n is 0, obviously square root of 0 is 0, so that's not a square root function at all, that's trivial. But if we then look at when n is negative, just to verify, now that n is negative, let's make it -1, we see that that is indeed the reflection in the y-axis. So that is, if n is -1, we're looking at the square root of -1 times x, so square root of -x. Obviously, if n is negative something other than 1, we have both a dilation from the y-axis and a reflection in the y-axis happening. Okay, so the negative is about the reflection, the size of the n value is about the dilation. But it's not dilation by a factor of n, it's dilation by a factor of 1 over n, the reciprocal. Okay, let me go back to the notes. Okay, so these are our new ones. Dilation from the y-axis. If we dilate from the y-axis by a factor of a, we actually have f of 1 on a. Okay, so if the dilation factor is a, the n value, the number in front of the x, is the reciprocal of a, 1 on a, and vice versa. If the number here is 1 on a, the dilation factor is the reciprocal of that a. Similarly, if we dilate by a factor of 1 over a, so we squash towards the y-axis, we'll have a in the function. Okay. All right, so if we have a look at that for our square root function, if we're doing f of 1 on a times x, we could also write that as x on a. We are replacing the x part of the function with 1 on a times x. So this would be y equals square root of 1 on a times x, or that could also be written as x on a. And that is a dilation by a factor of a, not a dilation by a factor of 1 on a from the y-axis. Similarly, if we dilate from the y-axis by a factor of 1 over a, it is f of ax, and again we're replacing x with ax, so for our square root function that is 1 over the square root of ax. It doesn't stretch it away from the x-axis, it squashes it towards the x-axis. Away from the y-axis, it squashes it towards the y-axis. Okay, so much like the translations to the left and right. So we know if we're translating to the left and right, f of x plus 3, that goes left by 3. F of x minus 3, that goes right by 3. So they're sort of backwards to what we think they should be. The same is true for these dilations. F of ax, so f of 2x, is a dilation by half from the y-axis. F of half x would be a dilation by 2 from the y-axis. When the transformations are inside the function f of something, they are backwards to what we think, what sort of intuitively we think they should be. Okay, so adding 3 inside the function is going to the left. Multiplying by 2 inside the function is dilating by half. Okay, we won't go into the algebra of how that occurs until next year, but for now we're just going to observe by looking at graphs that actually when we make that a value in here bigger, the graph actually gets thinner. So it's not being stretched away from the y-axis, it's being squashed towards. Okay, so let's use that knowledge then to sketch a couple of graphs here. So we've got y equals the square root of x pictured below, and we want to sketch the graph of y equals square root of 2x. So this one is going to be dilation by factor of a half from the y-axis, whereas this one is going to be dilation, I might use a different colour for that one, let's do that one in blue. So this one is going to be dilation by factor 2 from the y-axis. Okay, so I've got my blue pen. Let's dilate by a factor of 2 from the y-axis. So we're doubling all the x coordinates. So we're going to go, obviously 0, 0 is going to stay at 0, 0. Doubling the x coordinate of 1, 1 becomes 2, 1. We're going through point 4, 2. If we double that x coordinate, we're going through 8, 2. Obviously we go through, 9, 3, so that would be 18, 3. So it's going to be, heading right out there. Okay. You could take a few other points if you want. When x equals 2, this point gets dilated across to here. When x equals 3, dilated across to here. Okay. And you could pick any other point really. Look at about when x equals a half, going to get dilated across to 1. So that is y equals square root of half x, which might also be written as square root of x on 2. Let me just get those out of the way. Oh. Okay. If we have a look at the dilation by half from the y-axis, we're halving all our x coordinates. Okay, so we're going to come in here to half 1. This point at 4, 2 is now going to be at 2, 2. This point at 9, 3 is now going to be at 4.5, 3. Okay, the next major point would be 16, 4. That's going to come into 8, 4. So we're going to go through that point. And so this one would be the graph of y equals square root of 2x. Okay, dilation by half for the black graph from the y-axis, dilation by 2 for the blue graph from the x-axis. Okay, so once again, we haven't talked about this dilation from the y-axis before now, and that's because for all the functions before now, we can always manipulate the function first so that we're always thinking about a dilation from the x-axis as opposed to a dilation from the y-axis. We can also do that for the square root function. For example, y equals root 2x, we could, which is dilation by half from the y-axis, from y, just as an abbreviation, sorry. We could, if we wanted to, say that that is the same as y equals root 2 times root x, and therefore we could talk about it as a dilation by root 2 from x. Okay, you're multiplying the whole function by root 2. But multiplying by root 2 from the assert from the x-axis is more complicated than halving. So multiplying all the y values by the square root of 2 is more complicated than halving all of the x values. So in this case, it's not impossible to describe it as a dilation from the x-axis, but it's harder. When we get into much more complicated functions later on, if we're looking, for example, at the graph of y equals sine of x, if we dilate that by half from the y-axis, it is sine of 2x. There's no way for us to expand that 2 out of there. Okay, so we have to be able to think about these as individual transformations. So we haven't had to think about it before now. Let's have a look at some of the functions we've looked at. So let's have this example. We now know that y equals 2x all squared would be a dilation of the graph of y equals x squared. So if we think about f of x equals x squared, then f of 2x is 2x all squared. And we know that this is a dilation by a factor of a half from the y-axis. Okay, so if we were to take our graph of y equals 2x all squared and dilate it by half from the y-axis, our point at the origin is going to stay there. We're now going to go through half 1 and negative half 1. We're now going to go through 1, 4 and negative 1, 4. We go through 3, 9, so halving that is 1 1/2, 9, negative 1 1/2, 9. And we go through 4, 16, so halving that is 2, 16 and negative 2, 16. So that would be our parabola dilated by a factor of half from the y-axis. Okay. If we think about the expression y equals 2x all squared, we wouldn't write it like that. We would actually expand it out to 4x squared. So in this instance, we looked at what happened when we dilated by half from the y-axis. Okay. But actually, we know that y equals 2x all squared is actually exactly the same as y equals 4x squared, which is 4 times f of x, which is a dilation by a factor of 4 from the x-axis. So if we have a look at what happens, if we dilate each point by a factor of 4 from the x-axis, we're actually getting the same graph. Okay, this graph is also y equals 4x squared, which makes sense, they're the same function. But here we would think about it as a dilation by a factor of 4 from the x-axis, and here we would think about it as a dilation by a factor of a half from the y-axis. And for the quadratic, they produce the same graph. Okay, it's important to understand that a dilation by a factor of a half from the y-axis is not always the same as a dilation by a factor of 4 from the x-axis. It is just for y equals x squared. But similarly, if we think about other functions, so that's why we didn't think about dilating from the y-axis for the parabola, because we can always expand out the brackets. Whatever number we put in here, a times x all squared, is a squared x squared. So it's a dilation by a squared from the x-axis. So I've just got that summarised here in this first row of the table. If f of x is x squared, f of 2x would be a dilation by a factor of half from the y-axis, but if we expand that out, we find that for the quadratic, f of 2x is the same as 4 times f of x, which is a dilation by a factor of 4 from the x-axis. If we think about the cubic, if we dilated the cubic by a factor of a half from the y-axis, so it is 2x all cubed, we know we could expand that out. That's the same as 8x cubed, which is 8 times f of x. So a dilation by a factor of 8 from the x-axis is the same as dilating the cubic by a factor of half from the y-axis. You can try it, sketch them on axes, they'll produce the same thing. Okay. If we have the hyperbola, up until now we've been thinking about this as 1 half times 1 on x, okay, which is a dilation by half from the x-axis. Okay, so this is half times 1 on x. So obviously we think about this, we've replaced the x with 2x, that's a dilation by half from the y-axis, but we can also split it up and understand it as being the same as 1 half times f of x. So for the hyperbola, dilating from by a factor of half from the y-axis is actually the same as dilating by a factor of a half from the x-axis. And again, you could check that graphically. If we think about the truncus and dilating the truncus by a factor of 1 half from the y-axis, so replacing the x part of the function with 2x, again, we could expand out the 2x all squared on the denominator. So this is 1 on 4x squared, which is 1/4 times 1 on x squared, which means it's a quarter times f of x. So for the truncus, dilating by a factor of 1/2 from the y-axis is the same as dilating by 1/4 from the x-axis. And we've just been always thinking about them as dilations from the x-axis for these functions so far. As I mentioned previously, even the square root graph we could think about as a dilation from the x-axis. So dilating by a factor of 1/2 from the y-axis is f of 2x, which for the square root means square root of 2x. But we could expand that out by thinking about that as root 2 times root x, and so it is root 2 times f of x. And so for the square root graph, dilating by a factor of 1/2 from the y-axis is the same as dilating by a factor of root 2 from the x-axis. Okay, so for most functions, we can think about the dilation as being either from the y-axis or from the x-axis, depending how the function is presented or depending on how we manipulate the function. As I mentioned though, there'll be lots of functions. Exponentials will be other examples. If we've got y equals 2 to the power of 3x, we actually can't expand that out. If we've got sine or cos functions, we can't expand that out. We have to be able to think in terms of dilation from the y-axis. Okay, so now we've broadened our understanding of transformations. We've added in this n value in here, okay? And if we want to be able to accurately read off a sequence of transformations, we need to be able to write our function in this form. So that means if your equation is 2 times the square root of 4x plus 8 plus 5, that's a dilation from the x-axis by a factor of 2. That's h. No, sorry, I lie. That's the point I want to make. This is not in the same form as this. If you want to correctly read the dilations and the translations, you have to make sure that in the function, so in this case under the square root, the coefficient of x is factored out. So this is 4 times x plus 2 plus 5. So this is a dilation by a factor of 2 from the x-axis. This is n, dilation by a factor of 1/4 from the y-axis. This is h, we've gone to the left by 2, and this is k, we've gone up by 5. Okay, and we would do it in that order: dilations and reflections from the a and n values, and then translations. Next year we'll talk about how we can become a bit more flexible with the order, but for now we want to focus on get your function in this form, and once it's in that form, dilation and reflection first, and then translation. Okay, so as I mentioned earlier, when we're sketching some square root graphs and we want to do that, the first thing we want to decide is which of these 4 shapes am I dealing with. No reflections, reflection in the x-axis, so negative out the front, reflection in the y-axis, so negative next to the x, or both, so both of those negatives. So that's the first thing you want to decide. What shape am I dealing with? And then we can focus on any other transformations that are happening. Okay, so let's do some examples. Sorry, now we're getting into a long video. So we want to sketch the graph of negative 3 times the square root of x. Okay, so the negative out the front. So our shape, first of all, we've got the one reflection. Actually, let's just deal with that first. So our reflections are, we've got a reflection in the x-axis. And so that straight away tells us that our shape is going to be this one, going that way. The only other thing that's happening here is this 3. That's a dilation by a factor of 3 from the x-axis. It's out the front of the function. So it's going to be this shape here stretched a bit further away from the x-axis. So essentially it's just going to be this, okay? But we can't just draw that, because how do I know that that's not negative root x or negative 2 root x or negative 10 root x? So we're going to need at least one point on it. Let's just have a look at when x equals 1. You can do this in your head, but I'm just writing it out so you can see what I'm doing. When x equals 1, y is going to be negative 3 times the square root of 1, which is just negative 3. So if we mark the point, sorry, not negative 1, if we mark the point 1, negative 3, that tells us about the dilation. Endpoint is an important feature of a square root graph. It's at the origin, so we don't, conventionally, if we're going through the origin, we don't have to label that point as 0, 0. There's no reason you can't, but it's not necessary. Anytime that moves away from there, though, that endpoint must be labelled. Okay, sketch the graph of y equals half times the square root of negative x. So let's focus on those reflections first. This negative in here is going to mean we have a reflection in the y-axis. Okay, so in terms of shape, we're going out this way. Okay, The half out the front is a dilation by a factor of 1/2 from the y-axis. So it's going to get squashed in closer to the y-axis. When you haven't got another graph on the axes to compare it to, you can't really tell that it's been squashed in closer. But again, that's why we want to calculate a point. So we're going through 0, 0. Let's have a look at when x equals -1. If you were to put x equals +1 in here, the graph doesn't exist over there. So this time when x equals -1, y is half times the square root of -1, which is half times the square root of 1, so that's just half times 1, so half. So we can mark this point here as being -1, 1/2. Sorry, I squashed it in the wrong way, didn't I? I mean, it doesn't really matter. I've got another scale, but I'm going to draw it a bit flatter than that. -1, 1/2. Okay, so at least 2 points on your square root graph, including the end point. End point, all axis intercepts. If that doesn't mean you have 2 points, you need to add a second point, minimum of 2 points. Okay, let's have a look at number 5. Sketch the graph of y equals the square root of x minus 3 plus 5. There's no reflections here. There's no negative out the front, and there's no negative x. Okay, so no reflections. Oops, no reflections. So my graph shape is going to be this one, going that way. The -3 here is translating to the right by 3, and the +5 here is translating us up by 5. So we're going to take this shape and translate it right 3 and up 5. So our end point is going to move. Okay, so that means our graph is going to go to the right by 3 and up by 5. And it's going to go out this way. Okay, so therefore we're not crossing the axes at all, so we need minimum 2 points, so again we need another point. We want to substitute something past x equals 3, so let's substitute x equals 4, which means we're going to have y equals the square root of 4 minus 3 plus 5, which is root 1 plus 5, plus 5, so that's 1 plus 5, which is 6. So it goes through the point 4, 6. Now again, I probably want to think a bit about scale here. 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay, so 3, 5 and 4, 6. Up here, it didn't really matter where I put -1, 1/2, because there were no other numbers, 0 zeros here. So immediately by writing this point on here, I've defined that as being a unit of 1/2 on the y-axis, and that as being a unit of 1 on the x-axis. Okay, and so there's nothing else to compare it to maintain consistency. The issue if I kind of just go, alright, 3, 5, let's do that roughly there and draw a graph, is that if I mark this point as 4, 6, and this is 3, 5, I've now indicated that that's 3 and that's 4, so there's a bit of inconsistency there in the scale, and that's 5 and that's 6, and again there's a bit of inconsistency in that distance being 5 and that distance being 6. So if you've got more than one point, you just want to make sure your scale, it doesn't need to be perfect, it doesn't need to be measured, but it shouldn't be way out. You certainly shouldn't have the situation where you've kind of got that and you're saying that that's 5 and that's 6, in that that distance is much bigger than that distance. That would be a real problem. So just thinking a little bit about scale before you draw it on. Okay, example 6. Sketch the graph of y equals the square root of -2x minus 8 minus 1. Okay, first issue is in here. Remember, we need to have it as n times x plus or minus h inside our function. So we need to factor out the coefficient of x, so we've always only got 1x before we can then correctly identify what's the dilation from the y-axis and what's the translation left or right. Okay, so in this instance, we want to rewrite this as being the square root of -2 is a common factor, x plus 4, take away 1. Okay, so now we can identify, we haven't got a reflection in the x-axis, but we have got a reflection in the y-axis from this negative in here. Okay, so we're going to have reflection in y-axis, so our shape is going to be this one, going that way. And now we can correctly read off that translation. We're going to the left by 4 and down by 1. Okay. Alright, so left 4 and down 1. Just going to move that over a bit further. Left 4 and down 1. We're going to be sort of here. Oops, -4, -1. Okay, so in doing that, we've kind of defined scale there as that being 1, whereas on the y-axis that is a unit of 1. And that's fine. It doesn't have to be the same. It just have to be a bit consistent. So my graph's going to go out this way. So we're going to need to work out, we are crossing the x-axis, so we definitely need to work out the x-intercept. We need one other point anyway, and in this case it must be the x-intercept. So x-intercepts, we let y equal 0. So 0 equals, I'm going to go back to the original function, the square root of -2x minus 8 minus 1. We're focused on getting to x. Last thing happening on this right hand side is this subtracting 1, so let's add 1 to both sides. 1 equals the square root of -2x minus 8, and I find this is a common error that students make. If we want to get rid of the square root on the right hand side, we don't want to square root both sides. That's not what we're trying to do. The square root of the square root doesn't eliminate the square root. We want to square both sides of the equation to get rid of the square root. So we're going to have 1 equals -2x minus 8. We're going to add 8. 9 equals -2x. And so x is -9 on 2, which is -4.5, if that helps us. Alright, so we're going to be crossing, so if we continue our scale, that's sort of -5, -6, we're going to be crossing here. Okay, so that's going to be the point -9 on 2, 0. And we've got our end point at -4, -1. So we've got at least 2 points, including the end point and any axis intercepts. Okay, exercise 4C is the work for today.